Hello, welcome back on a gray Thursday. There's one handout today. That's the third and last programming assignment for the course. You'll probably be happy to know it's not in Verilog this time. It's in a language I hope you're all familiar with, C, and basically the idea is to do some simulations of caches and to evaluate performance of various different cache strategies, particular victim cache and pseudo-associative cache. We'll be talking about both of those. Is there a comment here? No. The midterms. The midterms are all graded. They'll be ready after class for you to pick up either here or outside. The statistics were as follows. The mean grade was 64. Standard deviation was 15. The minimum was 24. The maximum was 120? 96. So the standard deviation is actually fairly small. People seem to be clustered. I guess the major problem is that a lot of you ran out of time. It was too long an exam, as near as we can tell. Is that what you think? Yeah, see some heads shaking. The TAs took the exam and they finished it in an hour, so we multiplied by 2 and figured that was all right. So don't give them a hard time, and they've all seen it before and done it before, and helped making up the exams, made up a lot of the questions. So it's not a surprise, but we will take that into account in trying to do the final. The solutions to the midterm will be ready tomorrow on the news group, probably next Tuesday for hard copy, and probably for the SITN students next Wednesday for the hard copy. One handout. That programming assignment is due, as it says on the front cover, March 14th. So you've got 2.5 weeks to work on that, March 14th. We're going to finish off essentially pipelining and advanced computer design this time and move into memory system design. So for my show and tell today, I brought in an old memory board. This is in fact a core memory, and core, although nobody builds cores anymore, that the word still lingers in Unix commands and in the folklore and other such. This was about the last generation core memory ever made, because in fact this has IC drivers instead of transistor drivers, and I don't know the date of this, but I would guess that it's something like late 60s. And what's on one side of the board here represents 32K bytes. That's right, 32K bytes of memory. And at this point in its evolution, core memories were so small that you can't even see the individual cores with the naked eye. At least I can't with my naked eyes. And remember, the core memories are ferrite cores through which are threaded at least 3 wires, maybe 4 wires. So it's really rather incredible that they were able to get that kind of mechanical precision in a board like this. And this one is fraying a little bit. I think because this is so fragile, I won't hand it around, but I will leave it up here, and when you're collecting midterms, you can take a look at it. I also brought a 50-power microscope, a 30-power microscope, under which you can actually see the individual cores and see the wires that are threaded through them. So just be a little careful with it, because it's kind of fragile, and they're hard to come by these days. Even going to places like Haltech, you can't find core memories anymore. Okay. Last time we were talking about the DEC Alpha 21064 and its style of implementation for extreme high performance. And it was, and versions of it probably still are, the fastest microprocessor alive. And just to recap, the way they got that was to start with a relatively simple single-issue core that has a very deep pipeline. And because in deep pipelines, branch prediction, well, the cost of a mispredicted branch is extremely high, they want to do fairly aggressive branch prediction. Then take that core and add to it relatively simple superscalar features. Don't add any additional functional units. Try to issue 2 instructions at once. Don't do any register renaming. Keep the cycle time as short as possible, minimum gate delays between stages, and run the clock rate up as fast as you can. And power be damned, just make the clock click as fast as the gate delays between stages will allow. And that gets screamingly super performance. The 21064 and then later reduced mask version 21064A with some additional features were 2 original machines. There is now, or soon to be, a 21164 which follows basically the same design rules, takes it one step further, tries to do 4 issues per cycle instead of 2 issues per cycle. They are now adding additional functional units in the sense that they have 2 separate integer pipelines, so 2 integer instructions can be issued simultaneously to those 2 pipes. They have added a second-level cache on the chip. We'll be talking about caches later, but we've already mentioned multi-level caches. They have now level 1 and level 2 caches on the chip, and they've gotten the clock rate up to 300 megahertz. And this is also predicted to be a screamer, and probably at the time it's available, the highest performing microprocessor available. But it's big, 9.3 million transistors. It's very power hungry, 40 to 50 watts, which is a serious problem. Remember back to Cray and his statement that the most difficult problem in building fast computers was managing the heat, not managing the electrons, or managing the logic. It also has a consequence on the circuitry that surrounds the chip. The fact that the clock is that fast means that everything else surrounding the chip and the clock generation circuits has to be high performance, high speed, almost microwave design techniques. The memories have to be extremely fast. This certainly gets is a technique for making a very high performance computer, but it is not without cost. It's unlikely, for example, that you're going to be able to put a 21164 into a laptop computer because the power dissipation and heat generation is just too extreme. Yeah.
What effect does the high power?
Please, to the microphone.
What effect does the high power station have on the computer? The fact that it just has odd effects, undeterminable effects on
the question is, what effect does high power dissipation have? It's a mechanical problem more than anything else. You've got to be able to get the heat out of the chip in order to keep the temperature down. If you don't do that, then the temperature will raise up to the point at which the transistors go out of their design specifications. They can't run that hot. Their characteristics begin to change dramatically as the temperature goes up. So you've got to keep the temperature down, and the only way to do that is to pull the heat out as fast as possible, which means big heat sinks, fans, air cooling, maybe even fluid cooling, something like that. It's a mechanical refrigeration problem, and the object is to keep the temperature of the transistors down, because if it gets up beyond a certain point, then they fail to operate in the mode that they were designed to operate in. That's the DEC Alpha series. An entirely different approach to getting a high-performance computer is represented by the PowerPC series, in particular the PowerPC 604. And since you've all read the article that was included in the last lecture notes, you're an expert on this, and we can just hit the highlights. There are a couple of differences, some of which stem from the fact that they're implementing a different instruction set. This is still a RISC instruction set. It's still a load store machine, but it's a machine that has more complex instructions. For example, instead of just a displacement plus register mode of addressing, it also has a register plus register mode of addressing. And for both of those, they allow a kind of auto increment, that the result of doing that addressing mode can be stored into one of the registers for a subsequent instruction. So you remember from looking at pipelining that this requires additional ports for the registers in order to do the updates. It requires additional time in order to fetch more registers and do more operations before producing the address to memory. It's a condition code machine. It's not as bad as the old-style condition code machines because at least there are multiple condition codes that the software gets to choose to use, so you can do more clever instruction scheduling, but still that's a piece of state information that has to be worried about and handled in the machine. It has word, half-word, byte, and string instructions. It has, in floating point operations, composite instructions. You can do A times B plus C in one instruction, one 3-register instruction, which obviously complicates the pipeline. Given this kind of instruction set to implement, their choice, rather than go for a very deep, simple, high-speed pipeline like the DEC machine, was to go for a more complex pipeline, a more complex machine in general, with a much slower cycle time, but more things get done in each cycle. And in fact, this is a machine that combines a lot of the features that we've been talking about in the last couple of weeks. It has a reorder buffer. It allows speculative execution beyond 2 branches, so you can speculatively execute, save the results of instructions that may be 2 branches away from really knowing whether or not they're going to be truly executed or their results are to be saved. It does out-of-order scheduling, a Tomasulo algorithm or something very close to it. It's a superscalar machine, tries to issue, in best case, 4 instructions per cycle. So you can have one cycle where 4 instructions are being pushed into reservation stations in front of functional units at a time. It has, I don't know why I said some static, it has fairly aggressive dynamic branch prediction and load and store queues to mitigate the effect of going to slow memories. We'll talk more about the physical characteristics of it later. Let's take a look at the overall block diagram of the 604. This is actually not a picture out of the paper, but from somewhere else, but it shows more of the detail. Let's see where to start. The instruction cache provides to the decode and dispatch unit 4 instructions at a time. So 128 bits are going from the instruction cache to the decode stage. During iFetch, we'll take a look at the pipeline in a second, but during iFetch, it's trying to do branch target prediction. So before knowing anything about the instruction, as we talked about before for branch target buffers, they call this branch target address cache. That's what the BTAC stands for. They record in there whether or not the quad word being fetched out of the instruction cache is a branch that was successfully taken before. And if it was, then they have recorded the quad word of the next instruction to fetch. And in fact, this branch target address cache is a 64 element cache, which is fully associative, and we'll talk later about what that means, but that means that any saved branch can go anywhere in this unit. There's no conflicts between different places that things might be able to go. In addition to the branch target buffer, the branch target address cache, they also have a branch history table of the kind we were talking before. This is a 512 by 2 element branch history table. Remember, 2 is the way you can record whether a branch is really going to be taken or might be taken or might not be taken or really won't be taken. So it records that kind of history that tells you how strongly you know whether or not the branch is going to be taken or not. And they do that to be able to get a leg up on 512 of the branches, although this fetch can't happen as soon as it could if the branch were found in the branch target buffer. It certainly is better than waiting until the branch is completely resolved and you fully know the condition and the target address. This helps you at least with the condition, which is important because it's a condition code machine. They have a bunch of functional units, a floating point unit, a load store unit, 2 identical integer units for doing simple integer operations, and 1 more complex integer unit for doing multiplies and divides. And these buses that feed from the decode unit, in fact, can fill up a reservation station in each one of these units and also in the branch unit, which is a separate execution unit with reservation stations in front of it. One of the rules, and we'll see more of the rules listed later, is that you can only put an instruction in a reservation unit for each functional unit once per cycle. So if you've got 2 instructions that are both double precision floating point units, double precision floating point instructions that came out of the cache and got decoded at the same time, you can't issue them both to the reservation stations there at the same time, even if both reservation stations are empty. Basically one path from the decode and dispatch to the reservation stations for each functional unit. But if you've got one of each of these, then in fact you can fill up 4 reservation stations at once in one cycle. And in the next cycle, if those units are free, they will all begin execution at the same time. Now, one of the limitations you remember from the Tomasulo algorithm was this common data bus, that when functional units finished, they had to compete for storing results on the common data bus that would eventually go back to the reservation stations that were waiting to them or back to the register file. Well, in this architecture, in fact, they have duplicated what used to be called the common data bus, and they call them completion buses. And I think, in fact, that in this version, in the 604, there are 4 integer and 2 floating point common data buses, essentially, completion buses, where functional units broadcast their results. That's good, but also what that means is that every one of these reservation stations has to be monitoring all of the completion buses to see if the thing it's waiting for is on any of those buses. So again, lots of comparators. In addition to doing dynamic execution, this also does register renaming and also has a reorder buffer. So it gets the effect of precise interrupts, and it gets the effect of my mind just went blank. It gets the ability to do speculative execution, so that you can execute beyond a branch, and those results that might not be valid weren't written back into the register files. They were stored in the reorder buffer, and we'll see a bit more about that in a second. Let's look at the pipeline. It's got 3 stages for all instructions at the beginning of the pipeline. It goes through instruction fetch, instruction decode, and we saw the blocks for those earlier on. And then instructions go through issue. Now remember, 4 instructions can be going through this pipeline at the same time. So it's fetched 4 words in instruction fetch. It can decode 4 words, 4 instructions at a time. It may be able to issue, depending on limitations like the rule I just described, 4 or less instructions to the reservation stations in front of each functional unit. The integer functional units, of which there are 3, there are 2 simple ones and 1 complex one, have an execute stage, have a completion stage, and a write-back stage. In some ways, the completion stage and the write-back stage are very similar. In fact, during both stages, they can be writing results back to register file or actually reorder buffer. And in fact, if there are ports available, then the result can be written back during the completion stage. If there are ports not available, then the completion stage does some other functions, but doesn't do the write-back, and then delays the write-back until the actual write-back stage. So in fact, the pipe, in some ways, can be shorter than is shown here. During completion, in addition to an opportunity to write back registers, that's also the time at which exceptions are noted and recorded in the reorder buffer for being taken later. Branches go through just execute and completion. Load store goes through an address generate stage, doing the effective address calculation that I described before. Goes through a memory stage, doing cache access, and then completion and write back. Completion also does tag check for the cache. We'll talk a lot more about that next week. Floating point has 3 operational stages, a multiply, an add, and a round stage. And if it's a complex instruction, obviously, it takes more cycles than just those 3 before it goes to completion and write back. Now, what are the structures that this machine has to do all of the fancy things like register renaming and speculative execution, or recovery from speculative execution? Well, there are basically 3 different data structures. There are the reservation stations, and there are 2 of them, roughly, for each of 6 functional units. In addition, it has rename buffers, the rename buffers are structures that contain the original register number and eventually will contain the result value. So this is a way to be able to store the results without actually having to write them back to the architectural register file. Now, in some ways, it shares its function with the reorder buffer as we saw it. In this architecture, the reorder buffer, in fact, has no values in it, unlike the reorder buffer that we originally looked at, that keeps track of the values that are originally stored. Here, they split that into two functions. At the time that an instruction is issued, it gets an element in its reorder buffer. It gets a slot allocated in the reorder buffer so that the reorder buffer is always in order of instruction issue. But rather than maintaining a slot in the reorder buffer for the value, it points to a rename buffer where the result will eventually get put. And the rename buffer contains also the original register number so that when the reorder buffer gets to the head of the list, the corresponding result in the rename buffer can get stored into the register file. As before, exceptions are taken when they get to the head of the reorder buffer. There are precise interrupts, or precise interrupts can be implemented on this machine. The simple way of handling speculative execution would be to wait for the branch, which also gets an element, an entry made in the reorder buffer to it. Wait until the branch gets to the top of the reorder buffer. When it does, and it turns out that branch was incorrectly predicted, then you could wipe out everything in the reorder buffer in one cycle, do the refetch, and start all over again. The problem, as we noted last time, is that is a heavy penalty to pay for a mispredicted branch. So in fact, what they do, and that's why this description of things like the rename buffer is only approximate, that they keep extra information. So they tag the entries to indicate which branch they depend on. So as soon as the branch is known to have been predicted incorrectly, they can do a partial purge of entries in the reorder buffer and entries in the rename buffer that correspond to the instructions that weren't to have been executed. And in one cycle, as soon as the branch instruction has been resolved, in one cycle they can wipe out all of the partially executed results. So what are the rules for issuing instructions? Well, one is that each instruction as it gets issued needs an entry in the reorder buffer. It needs a reservation station for the functional unit that it's destined to, and it needs a rename buffer. So if any of those things are not available, then you need to stall. If that's not true, you can fetch, decode, and issue four instructions per cycle, but they have to be issued in order. The entries in the reorder buffer have to be done in the correct order, so you can't do out of order. At most, one instruction can be sent to each execution unit, which is to say to each reservation station in front of the execution unit, because there's only one path there, as I described before. And in addition, to handle this one-cycle flush of the reorder buffer and the rename buffer when the branches are resolved, a branch suppresses any subsequent issues in that cycle. If I fetched a word that has four instructions in it, and this is an add, and this is a load, and this is a multiply, and this is a branch, then in fact these are all, let's say this is a floating point multiply, these are all going to separate functional units, and the branch is the last in the word, so in fact I can issue all of those four instructions at once. But if there were a branch somewhere earlier on in the pipeline, like in the second, not the pipeline, but the quad word, if the branch were the second instruction, then I could issue the add, I could issue the branch, but these two instructions would not issue. Basically, the limitation is there can be only one branch per quad word that gets issued in one cycle. And that allows them more easily, it has to do with this tagging of entries with the branch on which they depend. It makes it much easier if, in fact, there's only a single branch with each parallel issue of multiple instructions. So that's one of the limitations that limits the number of simultaneous instruction issues. Now, one of the things you notice is that with an architecture like this, it requires a large number of ports for register files. You may be getting 4 instructions going through instruction issue at the same time, many of which are trying to fetch operands out of the register files. And in fact, register files and reorder buffers wind up having an awful lot of ports, and ports connected to each other. For example, the reorder buffer, sorry, the rename buffer has 2 write ports, both of which are feeding 2 read ports to the register file. So in fact, if you've got 2 instructions which are at the top of the rename buffer with results waiting to get written back to the register file, well, their entries are both at the top of the reorder buffer. The reorder buffer points to rename buffer entries, both of which are ready to be written back to the register file. In fact, for the integer register file, you can retire both of those instructions at 1 cycle. There are also duplicate structures for floating point. So remember that we're issuing, at best case, 4 instructions per cycle. We want to be able to retire, at best case, 4 instructions per cycle as well. So we can retire 2 instructions from the rename buffer and reorder file into the register file on 1 instruction in the integer side, do 2 more on the floating point side. So if everything is working exactly right, then in fact we can retire 4 instructions and issue 4 instructions in every cycle. Now obviously everything doesn't work entirely right most of the time. So let's go through an example of, again, one of our famous simple loops to see how much overlap we get and how much parallelism we can expose in this program. Again, it's trying to add a constant to a vector and store it in another vector. And here we can use a couple of the special features of the PowerPC instruction set architecture. One is the auto-increment addressing mode, and the other is that they have a special branch loop counter, basically a register that is designed for doing loop closures that decrements the register by 1 and branches if it's not 0, which is a great kind of instruction because it's easy to do prediction on an instruction like that. You know always what the future value of that register will be. It's always r minus 1. So the instruction sequence is load floating point value into register 2 from wherever register 1 is pointing to and auto-increment it. What this really is one of these d of r1 fields going to r1, where d is equal to 1. So it's a kind of displacement mode, or it could be a register plus register mode where one of the registers is 1. So it's not quite the auto-increment of the VAX, but in this case, if you set up the registers correctly, it has the same effect. Floating point add, the constant C preloaded in register 0, do the store. The store does the same kind of auto-increment mode, and then the counter branch. So we've got a 4 instruction loop. Well, we can certainly fetch all 4 instructions in 1 cycle, decode all 4 instructions in 1 cycle. We can issue the load. We can issue the add. We can't issue the store because the load was already used up its quota for issues to the load store unit. So the store has to be delayed 1 cycle. And because the issue of the store is delayed 1 cycle, the issue of the branch is delayed 1 cycle. Remember, we have to have in-order issue. It's got to make entries in the reorder buffer in the order in which the instructions are being executed. The load proceeds without any stalls, obviously. Instruction fetch, decode, issue, address generation, cache reference, completion, tag check, results back usable from the memory. At this point, it can forward its results to the multiply. Now, forward in the sense that it puts the result of the load on the completion bus, and the add waiting in the reservation station, because it's already been issued, picks it up, and then can go through its multiply, add, and round sequence to produce the result. The store can get issued. It can do address generation soon. And in fact, that's good because it gets to retire register 2, which has to be rewritten early on, making it available for subsequent instructions. But it has to stall until the result of the add gets forwarded to it, and it can do its cache cycle. The branch instruction got issued. In fact, it was probably likely that the target was detected in the instruction fetch stage because it was a hit in the branch target address cache. And in fact, probably the next quad word of instructions didn't get decoded and fetched here, but got decoded and fetched a cycle early. So in fact, probably moved those two a cycle earlier. In fact, it doesn't make any difference. We're not going to be able to go any faster because this load can't get issued until cycle 5. It's got to be, issue after the branch. It proceeds in order. We've got the same read after write hazard here, the same read after write hazard here. And at this point, you can see, let's see, by looking at multiply versus multiply, for example, that the steady state for this loop is 2 cycles per loop, which is a lot better than the alpha chip, which was, what, 7, 9 cycles per loop, something like that. But these cycles are obviously taking a lot more time. The clock is much slower. It gets a fair bit of parallelism. We've been able to fetch, although not issue, 4 instructions in parallel. We've been able to issue 2 instructions in parallel. So it's working pretty well. Obviously, still a lot of stall cycles, but good performance nonetheless. Question is, how good performance? Yeah, question? Yes, I think that's true. The alpha example was not well optimized, so if we did some clever scheduling and unrolling there, we could get its performance better. On the other hand, for this machine, we didn't have to do that. So you can count that as an advantage, I suppose, that the machine does really well, or reasonably well, on naive code that didn't have to be optimized. But you're right. And in fact, DEC has some great compilers to do a lot of good scheduling and performance engines. Yeah. Uh-huh. The load into R2 in the store, yeah. There are 2 different register 2s here. The store instruction is using integer register 2 as the address. The load instruction is loading, oh, I see, there's a bug here. The load instruction is loading floating point register 2. Is that the problem? Okay. Yeah, this is a floating point loop, remember. So the load is loading a floating point register, and the add is operating on floating point registers, and the store is using fixed point register 2. I got it right on the second one. Sorry about that. Obviously, you can tell I didn't run these programs. So the PowerPC 604, summary. It's the first microprocessor to have the stuff that mainframes had 30 years ago, which is to say true dynamic scheduling, speculative execution, Tomasulo-like algorithms, that sort of thing. It's a lower clock rate machine, has lower power dissipation, which has advantages as we described before. The 604 has been around for a while. The next version is the 620. These machines leapfrog each other, obviously. In the 620, they've done a lot to fix branches, and that implies that they were broken. They weren't broken. They are doing a lot to make them go even faster. They're trying to speed up the clock. They're going back to a more conventional 5-stage pipeline. So the penalty per mispredicted branch is now 2 cycles instead of 3 cycles. As a way to make branches go faster, they're quadrupling the size of the branch structures, the branch target and the branch hit structure. They allow 4 reservation stations instead of 2 for a lot of the functional units. The same algorithms, basically, a kind of standard next generation, make everything a little bit bigger and faster. This is a summary table that shows the 2 stages of the PowerPC and the 2 stages of the alpha. And they're leapfrogging each other. If you believe these spec int numbers, that in fact the PowerPC 620 will have higher performance than 21064A. Remember, the A was already the second version of the alpha that had gone down to half micron features from I think it was 0.7 micron features. But the 21164, with its higher clock speed and even more features, will be predicted to be up in the 300 spec int range or something like that.
Question?
Yeah.
What about the power consumption of the PowerPCs? We haven't mentioned that at all.
It's the power consumption? It's way down compared to the Alpha. It's probably on the order of 20 watts. I don't know if does anybody have a better idea? It's probably half or less the power dissipation of something like the Alpha.
620 is 20 to 30 watts. The 604 is 10 or less, about 10 or so, maybe less.
Okay, and the 21164 is something like 50 watts?
Yeah.
Right.
21064A is 30 plus, 30 to 40.
Right. So a big difference. And also remember a big difference in the surrounding circuitry, because in order to get memories and caches and clocks and buses and so forth running at 250 to 300 megahertz, it's a different design ballgame. This is not an electrical engineering course, at least not at the circuits level, but going from 100 megahertz to 300 megahertz introduces all kinds of additional radiation problems, transmission line problems, and it changes the qualifications that the designer needs to be able to design a board to work on a chip with a chip like that. Okay, those are fast RISC machines, but what about, remember that old x86? A machine that everybody hates, but 85% of the computers in the world are using? How do you make a machine like the x86 run fast? Amazingly enough, people have done it, and I just want to take a fast look at the AMD K5, which is one of the latest machines that implements the x86 instruction set, yet tries to take advantage of all of the features that we've been talking about. It's a 4-issue superscalar, it has out-of-order execution, it does speculation, it does register renaming, and it does all of that for the complex instruction set, which is the x86. It's actually pretty amazing. And Intel, in fact, just last week, David was telling me at the ISSCC conference, announced their P6, which is a comparable machine that has comparable ideals for performance on this instruction set. One of the major problems is that the instructions variable length. So you don't know where the next instruction is until you have decoded the previous instruction. That makes it very difficult to fetch 4 instructions at a time and issue them simultaneously and get them executing simultaneously, like we did with the RISC. Well, how do you fix that? Well, one way they fix it is to pre-decode instructions. Now, instructions, if we're doing things well, come out of a cache anyway. There's no reason why that cache has to contain only the instruction. You've done that instruction before, otherwise it wouldn't be in the cache. Why not store in the cache additional information that you can use to get those instructions issued a lot faster? And in fact, K5 does that. It stores 5 bits per byte in the instruction cache that indicates a whole bunch of things, including whether this byte is the beginning, middle, or end of an instruction, so that it knows when it's fetching, I don't know how many it fetches, 16 or so bytes in parallel from the instruction cache, where it should be doing the decode, where the subsequent instructions in that wide word starts. In addition, this is sort of the standard mathematical approach to solving a problem. You reduce it to a problem that's already been known. We know how to execute RISC operations very fast. So one way to make a fast x86 machine is to translate on the fly the x86 instructions into RISC operations and then do what we did before, build a machine that executes RISC instructions fast with speculative execution and out-of-order execution, dynamic scheduling, and all of that. So in fact, they translate 16 bytes at a time of these pre-decoded instructions to these so-called ROPs, or RISC operations. And then they can issue up to 4 of the ROPs per cycle and schedule it through a 6-stage pipeline and have branch histories just as we did before. Basically, they're executing a RISC machine on the inside and a complex instruction machine on the outside. This actually is very similar to a technique which got dropped from the beta edition of the book, a technique called microprogramming, which has been used for many years in various different forms for implementing instruction sets. And I think I'd like to spend a couple of minutes just talking about microprogramming and what it does and why it's coming back. Basically, when you're designing the control structure for a machine, there are two standard ways of doing it. One is that you can build state machines for a multi-cycle computer that tells you how to go from state to state to state in the execution of an instruction. Or you can build a computer inside the computer, a microcomputer that itself has little instructions that get executed that tell you what to do in the execution of each of the outer level or macro level instructions. And you can do this for one of two reasons. One is that it simplifies the control logic in the machine. It allows you to reduce it to a software problem in some sense, embed all of the sequencing logic into software rather than building it out of hardware state machines. The other is it allows you to build a machine that can be changeable. In fact, this doesn't tend to be in fashion anymore, but back in the 60s and 70s, it used to be fashionable to build microprogrammable machines that could then emulate other machines. Because you were about to obsolete those machines or for whatever reason. In fact, the early versions of the 68,000 computer were internally microprogrammed machines, and IBM was working with them to make versions of microprogrammed 68,000s that simulated the IBM 370 instruction set. Though it's a technique that's been used for a long time and is now coming back for complex instruction sets like the x86. Basically, in an outer level machine, you have a bunch of registers and ALUs and caches and multiplexers, all of which have to get controlled. You build inside that machine an inner level machine that does all of the control for those objects. And the inner level machine looks like a standard computer in the sense that it has a memory. This is the instruction memory or micro instruction memory for that computer. It would typically have a standard kind of program counter that gets incremented by 1. May also have other ways of specifying the location within this micro instruction word, like a decode table. One of the things you want to do is to be able to get to the right place in the micro instruction memory really fast based on the opcode. So you could have a built-into hardware opcode decode table that says, based on that opcode, here's the program counter to start execution from in the micro instruction set. The micro instruction is typically a very wide word. This might be 100 bits or something like that. And each one of the individual fields controls some specific piece of hardware in the machine. So this might be a ALU function field that says what a particular ALU in the machine should be doing. This might be a multiplexer control that says where bits are to be shuffled around into the register file from, and so forth. And some of these fields can be tightly encoded, and some of them cannot be, might not be. Horizontal microcode was typically a very wide word microcode that had very few encoded fields. There might, in fact, be lots of individual bits in these words that go to control individual latches or individual AND gates within the machine. An alternative is the more vertical structure, which had narrower words or shorter words, where more of the fields were encoded, and you can do fewer things in parallel. This kind of structure actually should begin to look a little familiar, because in some ways it's very much like the very long instruction word architectures we took a look at. You can think of a very long instruction word machine as a microprogrammed machine where you're doing the microprogramming directly, rather than using the microprogram to interpret a more complex outer level instruction. In the case of the K5, they're using it in a more conventional sense of an inner machine that's assisting them in the decoding of a more complicated instruction set. And if you look back here at how they do the translation, they basically have two different approaches. One is if it's a very simple target level instruction, if it's an 8086 load or move instruction, or probably even store instruction, then they know that it's only going to take one or two or three of these simple RISC operations in order to do it, and they do a direct translation at the time they do the issue into those RISC operations, and then they schedule those RISC operations in the way we've been talking about for the last couple of weeks. If it's a more complex instruction, like one of the string moves, then in fact they have a ROM. They have a microprogrammed ROM out of which they fetch a sequence of these ROPs and treat it just like a conventional, old-fashioned styled microprogrammed computer. Take a look at the block diagram of the K5. And you can see it's actually relatively simple. The instruction cache, which for the K5 is 16K, contains pre-decode information that we talked about, those 5 bits per byte. So they're fetching 128 bits of instruction information and 80 bits of pre-decode information. And for the simple instructions, they do an immediate translation to one or more of these RISC operations. And then from here on in, it looks like a standard RISC computer. They have multiple functional units. Functional units can execute in parallel. They have more than one load store unit, and so forth. They allow out-of-order execution. There's a reorder buffer that controls writing words back into the register file. Basically, this 80% of the machine is a standard RISC high-performance pipelined speculative execution machine. And this part of it up here is the part of it that efficiently translates the x86 instruction set to RISC operations. Any questions? Any comments? Okay. That is the end of a major section and a chapter in the book. And what we're going to start talking about now is memory. We've gotten the processor going about as fast as humanly possible. The problem now is that the memory isn't fast enough. We've been making this assumption that our cache memory will go at 1 cycle per, and if we get a cache miss, well, we'll do something. Well, now we have to figure out how to design caches to make that feasible and to figure out what the something is when the cache misses. So here's an outline of the next couple or maybe 3 classes. Basically, we'll talk about different cache memory designs. We'll look at some, again, simple back-of-the-envelope kind of analysis to figure out how well they perform. And then we'll look systematically at a bunch of different ways to reduce the penalty associated with caches and improve its performance. Then we'll talk about main memory. After all, after you get a miss in the cache, you've got to do something going to main memory, and there are lots of techniques in designing main memory systems to make them run faster. And then we'll talk about something that we've managed to ignore all of this time, which is virtual memory, the way that physical addresses and programmer-visible virtual addresses differ, and what the translation between them is, and what hardware structures one needs to do that. And it turns out that virtual memory by itself is an interesting topic, but is particularly interesting when you consider the cache. And getting the cache to run fast at the same time the virtual memory is running fast is a bit of a challenge, and we'll see why that is. Notice that we are pushed into doing this because memory isn't getting fast enough. Processors are getting fast. Memory is getting cheap very fast. If you look over the last 30 years, the cost of memory has come down about 1 million-fold, but the speed of memories has come down only about 20-fold or something like that. So what do? Well, you use some of these techniques to make up for the fact that it's not fast as you'd like. We haven't noticed made memory for a typical computer 1 million times less expensive. Of this 1 million in reduction, we've used maybe 100 of it or a few hundred of it to reduce the cost of the memory in a typical machine, and use the rest of it, the other 1,000 or 10,000-fold increase, to put more memory into each individual machine, which is probably a good trade-off. Okay, this is all a review. I'm sure you understand this. Our pipelines of assumed memory access takes 1 cycle time, and obviously it doesn't. It could, if you were willing to spend enough money to use a lot of fast memory, the fastest memory that money can buy in your computer, but you can't because it costs too much money, it takes too much power, it takes too much space, you can't fit it on the chip. Even if you build special purpose fast memory chips, when you accumulate enough of them together to make as big a memory as your system wants, the system memory performance is slow. You can't, it's hard to put together even fast chips to make a really fast system-wide memory. So fundamentally, the big memories have got to be slow, even if you're willing to spend a lot of money. So the obvious trade-off is to use a hierarchy of memory where you put the small, fast, expensive caches at the top of the memory hierarchy and the large, slow, and cheap memory down at the bottom. And the idea is to make it as cheap as the thing at the bottom and as fast as the thing at the top. Well, you can approach that, obviously not achieve that. The reason why it works, and I'm sure you've seen this a zillion times, including briefly at the beginning of this course, is because of program locality. Spatial locality says that addresses near ones recently referenced are likely to be referenced again. Instruction fetches and array references have that property. And temporal locality says if you reference something, you're likely to reference it again soon. Variables and stacks have that property. People used to talk about the working set, which is if you look back in time for a constant distance in time, in the last millisecond, how big is the set of instructions and data that program referenced. That's the working set of the program, the non-contiguous set of addresses that it's been using most recently. And in fact, if you define it the way I described, which is all of the references made in the last 10 milliseconds, say, then it's not a constant size. The size of the working set varies depending on what the program is doing. Unfortunately, caches can't have that property. Caches are a fixed size, so the amount of the working set that the cache is actually able to capture will vary over time depending on what the program is doing. Okay, here's a depiction of the levels in the hierarchy. We're talking mostly about caches, but you can consider in any of the stages in this hierarchy that each level is a cache for the level before it. And starting with the top, registers are a form of cache that caches information in very high-speed memory that otherwise would appear in the memory cache, in the level 1 cache. And the distinguishing property of registers as a cache is that the compiler manages the transition of data from registers to the memory caches. At the next level down, hardware manages the transition of information between the caches, level 1 and level 2 caches, and the main memory. As you go further down in the hierarchy, in fact, it reverts back to software. You can view the disk in a virtual memory machine as the main memory, and in fact, the primary memory. I'm using main in two different senses here. And the main memory, the dynamic read-only memory, typically implemented type memory, is a cache for the disk. But in that case, again, it's managed primarily by the operating system. Obviously, the hardware does some detection of the case when you have a cache miss, which is to say a page fault, but then the operating system is involved in doing these transfers. And similarly, you can view, especially for some long-term processes like database applications, that the ultimate storage for the data is on tape, and that the disk is only a temporary cache for that information. And again, the operating system and the applications are doing the management there. Typically these days, the first two levels, that is to say registers and the level 1 cache, are contained directly on the CPU chip. The level 2 cache in the main memory is on the board, or on the boards that make up the system, and after that it's on peripheral equipment. Although, as we noted, sometimes, in fact, level 1 and level 2 caches are both implemented directly on the chip as part of the microprocessor. What are the numbers, rough order of magnitude, of how much and how fast and how much it costs for each of the various pieces? Well, 512 bytes might be right for a register, 32K bytes for a level 1 cache, 512K bytes for a level 2 cache. Obviously, these numbers are scaling a factor of 2 roughly each year or something like that. And any self-respecting computer these days has to have at least 32 megabytes of main memory. 2 gigabyte disks, that's probably low, in fact. It's probably more like 6 or 10 gigabytes of disk. After all, a gigabyte of disk down at Fry's only costs, what, $400 now, something like that. Right? And tapes are, individual cassettes are up in the 10 plus. Plus, notice, because tape is the only one of these things that's fundamentally unlimited in its quantity, because you can have as many tape cartridges as you like. Speeds are as shown. Notice that there's a big dichotomy, or big breakpoint here between the speeds of semiconductor memories and the speeds of mechanical memories going down to disk. And that causes a real headache and a real focus on getting main memory page miss rates to be as slow as possible, because the miss penalty for this cache transition from main memory to disk is a big step down, and not as big as the penalties in some of the other cases.
Is that figure for L2 caches typical of L2 on-chip or L2 off-chip?
It's typical for L2 off-chip. L2 on-chip typically is not as large as that. Costs, as near as I can plot them at this point in time, are about as shown here. Very hard to say what it costs you to put cache in the level 1 cache in the processor, or how much it costs you per register bit, because it's a complicated function of area and what else you would do with the area for those structures at the same time. You're not paying on a per bit basis the way you are for memory chips and disks and tapes. These kinds of memories for level 2 caches are typically static random access memories. Main memories are typically dynamic random access memories that have higher density, lower cost per bit, but not quite as good performance. Okay. Well, let's look at caches in a little more detail. Some terminology first. The terminology we've been using is that lower levels are closer to the CPU. So the CPU is directly connected to the level 1 cache, which gets connected to the level 2 cache, and so forth. Now, in some fundamental sense, all of these caches just have bytes in them, but the bytes are divided into words, and the words, not divided into, combined into words, and the words are combined into blocks. And at each level, a block is the minimum amount that is at least checked for. It's the amount that you're going to keep a little directory information for that says what data is actually in that location. In many cases, it's also the amount that's transferred. So a block in a cache might be, it's almost always power of 2, it might be 16 bytes. You check to see whether the byte you're looking for, or the word you're looking for, is one of those 16 bytes. And if it is, you transfer that entire block to the next level cache. We'll see some techniques, in fact, where although the amount checked for is a block, the amount transferred might be less than a block. So they're almost always powers of 2. Usually it's the case that at higher levels, at the slower caches, the block sizes are a multiple of the block sizes at the lower level, at the closer to the CPU levels. And there's some good reasons to do that, and we may be able to talk about that. But then the structure of a memory address at any level is particularly simple. There are some number of low-order bits that represent the byte offset within that block, and then high-order bits that represents the block address within that cache. At any level of the cache, you attempt to make a reference to the cache. The hit rate is the number of times you discover that that data is in the cache divided by the number of times you attempted to make a reference at that level, and the miss rate is 1 minus the hit rate. Usually it's the case that the access time of a hit, the hit time, is the same as the misdetermination time. It takes you the same amount of time to determine that the value isn't there. I guess that's fairly obvious. Now, when it's not there and you have to take a miss, then you can look at 2 different components of the time it takes to cover up for that miss, the miss penalty. One is the time it takes to begin the transfer, the initial access time, which is looking up the data in the next level cache. And then the time that it takes to transfer that complete block, and it may be a multiple word transfer or a multiple block at a next lower level transfer into the cache. So the initial access time is constant, and then the transfer time for the entire block or the entire line is a function of the block size. By the way, many people refer to line what we're talking about here as blocks. So if you see people talking about cache lines and cache blocks, they're basically the same thing. Okay, all very simple stuff. Let's look at some simple calculations of a memory hierarchy performance. A miss rate, which is what we've been talking about so far, remember, is only one component of the performance, because it tells you the rate, it doesn't tell you what the penalty is, it also doesn't factor into the equation what is going on in the CPU and how significant these misses are in terms of CPU performance. But the first step in getting to a more accurate performance measurement is calculating the average memory access time. And we saw this stuff earlier on in the course, so I won't need to go over it in detail, but the average memory access time is the time it takes to do a hit, which is also the time to determine that it's a miss, if it is a miss, and you add to that the percentage of times that you've missed times the cost that it takes you to do that. Now, if it's a two-level cache, then there's a hit time that you always have to pay for the first level memory. Then there is some cost for having missed in the first level cache multiplied by the number of times it happens. The cost of missing in the first level cache is a composite of two things. One is how long it took you to hit in the second level cache if you hit, which is the same as how long it took to determine that you didn't hit in the second level cache. And in the case where you didn't hit, that fraction of the time, you have to pay a miss penalty in the level 2 cache. So let's make up some numbers. Let's say that the level 1 cache costs you 10 nanoseconds if it's a hit, and 90% of the time you get a hit. If it goes to the level 2 cache, let's say that 95% of the time it hits in the level 2 cache, and it costs you 100 nanoseconds to do that. And if you missed in the level 2 cache, then it costs you 200 nanoseconds to go to main memory. So the average memory access time is 10 nanoseconds for the level 1 cache. 10% of the time, which is 1 minus 90, that you missed in the level 1 cache, you have to pay the penalty. That penalty is always 100 nanoseconds for the level 2 cache. And sometimes, 5% of the time, an additional 200 nanoseconds. So the total penalty is 21 nanoseconds, or the total average memory access time, rather, is 21 nanoseconds. Twice as much as if everything were in the level 1 cache. Now, in fact, it's interesting that this example shows a 95% hit rate for references that got past the level 1 cache and you're trying to find in the level 2 cache. That's not typical, and we'll see in just a second why that's not. That would require an enormously large level 2 cache. It's more typically the case that level 2 hit rates are in fact quite a bit less than level 1 hit rates, because you've already taken a very good shot at it by looking at the level 1 cache. But let's take a look at, in fact, comparing two caches and looking at how you might combine the two caches and see what the effect is. Let's say that we have a level 1 cache, like we had before, with a 90% hit rate. Hit time is 10 nanoseconds. Say that the miss penalty in this case is 180 nanoseconds. So the average memory access time is 10 nanoseconds plus 10% of 180 nanoseconds, or 28 nanoseconds. Okay, in the next case of this level 2 cache, if you were to use only it instead, it's got a higher hit rate. Let's say it's a bigger cache, so it only loses on 5% of the accesses. It's got a bigger hit time because it's a bigger cache. And let's say that the miss penalty is the same. So in this case, if you were only to implement the level 2 cache, then you would pay 20 nanoseconds plus 5% of 180, or 29 nanoseconds, almost the same amount. Right? Higher hit rate, but slower access time. Well, what happens if you try to combine both of them? Well, 10 nanoseconds in the level 1 cache, 10% of the time you miss in the level 1 cache and have to suffer the level 2 cache penalty. Level 2 cache penalty is 20 nanoseconds plus 5% of 180 when level 2 cache misses. So it looks like it's 12.9 nanoseconds, which is an enormous win. You believe it? Somebody's shaking his head. Well, I believed it about 1 o'clock in the morning when I was making up this slide, but this is wrong. In fact, you don't get that much of a win, and the reason is that this hit rate is the so-called solo hit rate. It's based on this as the only cache in the system. And in fact, if you put the two caches in front of one another, the level 2 cache is only going to see those items that were not found in the level 1 cache. So it's not going to be seeing all of the references. Most of the references that represent its 95% hit were in fact already trapped by the level 1 cache. So its hit rate is going to be a lot less than that. Let's say that the CPU is generating 100 references. 95% of those references are going to be found in the level 1 cache. 10 of those references are going to be head on to the level 2 cache. If we had only the level 2 cache and hit the level 2 cache with all 100 of those references, 95% of them would be in the level 2 cache. 5% of them, or 5 of those references, would be misses in the level 2 cache. The level 2 cache, when it follows the level 1 cache, only has a 50% hit ratio, not a 95% hit ratio. Big difference. Yeah?
But you wouldn't be pushing stuff out of the level 2. It would have different things in it, right? So it doesn't seem like
yes and no. One of the things that I've assumed here is the so-called inclusion property. I'm assuming that in fact everything that's in the level 1 cache is also in the level 2 cache. Right? And we'll talk more about this later to say why or why not that's a good idea and in what cases that happens. But I'm assuming in fact that level 2 is small, level 2 is big, and level 2 is a superset of level 1. There are lots of reasons why that's a good thing to do, and there are lots of easy ways to make that happen. But if you grant me that, then I think this analysis is right. At least I did it in the morning when I was a little more awake. And now we can compute the correct average memory access time. It's still 10 nanoseconds for a hit in level 1. It's still 10% of that costs 20 nanoseconds for the lookup in level 2. And now, in fact, it's 0.05% of the time when level 2 misses times 180 nanoseconds. Total of 21 nanoseconds. Let's see, another way to look at this is, let's see, do I have this right? Yeah, 0.05% of the time. These 5 references out of these 100 references are the ones that are missing out of the level 2 cache. It's not 0.1 times 0.05, which was what we had before. It's 0.05 times 180 nanoseconds.
But you're missing a 0.9 in front of the 10?
We're missing a 0.9 in front of 10. This 10? No. This is this 10. It's the hit time for the first level cache. You always have to look at the first level cache first. That costs you 10 nanoseconds. 10% of the time, you're going to go to the level 2 cache and cost 20 nanoseconds. 5% of the time, that level 2 cache is going to miss and cost you 180 nanoseconds. Make sense? Okay. I hope this is right. If this is wrong, come beat me up about it. We're just about out of time. And next time we will talk about cache design in detail. Midterms, yes. Midterms will be up here. Alphabetical order.